To get a better understanding of who I'm speaking to, so just by a show of hands, who here has heard of Kaggle before? Awesome, so almost the entire audience. Now keep your hands up if you have a Kaggle account. Looks like about half the audience, 40% of the audience. And now keep your hands up if you've made a submission to a Kaggle competition before. Roughly 10% of the audience, it looks like. And let's see, are we live? Yes, we're live, awesome. So for a bit of background, as it looks like many of you know, Kaggle runs machine learning competitions. We got started about 5 years ago, and since then we've run hundreds of machine learning competitions, and we release these challenging machine learning problems to our community of about 410,000 data scientists and machine learning engineers. Then just to give you a sense of the scale that we're currently operating at, our community now makes about 100,000 submissions per month in these competitions. And to give you a couple examples of the types of competitions that we run, here's a couple of my favorites that we've run historically. One's on automatically grading student-written essays. So we're releasing a data set of about 21,000 essays from middle and high school students to our community, and then challenging them to develop algorithms to automatically grade these essays. And the end result of this was actually the algorithms the students, our community developed, worked as well as the human graders and were as reliable as the human graders on these essays in the state standardized exam scenario. Another example is predicting a compound's toxicity given its molecular structure. And this was in partnership with Boehringer Ingelheim on early stage drug discovery pipelines. In this case, in about a 3-month period, it resulted in about a 26% improvement on the previous accuracy benchmark. In the web domain, one example is on personalizing web search results, which was in collaboration with Yandex on about 167 million web search logs from users in a couple different cities in Russia. And this resulted in about 3,500 submissions over a 3-month period. And one of the ones that closed most recently, and one that I was really excited about, was on automatically detecting diabetic retinopathy. For those of you who aren't familiar with diabetic retinopathy, it is one of the leading causes of blindness in the first world countries, where and it's very tough to diagnose in its early stages and requires a really highly trained ophthalmologist to diagnose. And this is applying computer vision algorithms to grade or score someone who potentially has diabetic retinopathy. And then the end result of the competition had about 85% agreement with a human grader, which was absolutely phenomenal. And anything north of about an 80% agreement is considered a really good thing for iterator reliability. So that gives you a sense for some of the types of problems that we're looking at solving through machine learning and machine learning competitions. Now let's dive into how these competitions work. We take a data set with a target variable or something that we're trying to predict, and this will be a heavily stylized, simplified problem. But let's say I'm predicting the sale price of a house. So I have the sales price and a couple features describing it. And then I'm splitting the data into 2 sets, a training set and a test set. And then giving our community everything but the solution on the test set. So they have the training data, then they have the test data, but they don't have the answers on the test set. And then the community then takes the training set, then uses that to learn the relation between the data and the target. And competition participants apply their models to make predictions on the test set here, and then they then give us those predictions as a machine learning model submission. And then we go and compare those results to the ground truth, calculate 2 different error metrics on it, one on a public subset of the test set that they get feedback on immediately, and the other on a private subset that we use for final evaluation. So very immediately, the participant sees their public score on the leaderboard and how they're doing compared to the rest of our community. And this is one of the most powerful incentive mechanisms that we have in place, and I'll talk about that more in a bit. And then as the competition progresses, participants continue to explore the problem and iterate on their models to improve them. And then at the end, the best score on the private leaderboard wins, and that's the only point in time that we evaluate participants in the private set. Now let's look a little bit more at this leaderboard mechanic and how it works. So it's a very powerful mechanism to drive a competition. First, it's very objective and meritocratic. Every person is being compared on this using the exact same methodology and on the same data set. Secondly, it encourages leapfrogging. So as one participant sees another participant pass them, they'll be incentivized to try spending the extra effort and passing the other participant more. We call this the Bannister effect. For those of you who aren't familiar with the story of the 4-minute mile, for a very long time, people thought it was physically impossible to run faster than a 4-minute mile. And then Bannister was the first person to break that barrier. Then once he broke that barrier, very quickly, dozens and dozens of other people also broke that barrier. So in many senses, it was a psychological barrier instead of a physical barrier. And once you have evidence of someone being able to break it, then that pushes other people to break it as well. And this also relates to the number of improvements people make over many submissions. In a lot of problems, if you start on the problem, you make a good first pass on it, then you say, okay, I did a good job and called it quits. In this dynamic, you keep iterating and iterating and trying to improve your previous result and beat yourself. So that encourages many submissions as well as ongoing and iterative improvements to a model. And to give you a sense for how this operates on a single competition, at the beginning of the competition, usually performance improvements are characterized by rapid improvements to the underlying problem and error metric with a lot of leapfrogging. And then as time progresses in the competition, by the way, the x-axis here is time from the start of the competition to the end of the competition, and the y-axis here is model performance with bad being on top and good being on bottom. We very quickly see, as time progresses, we hit a frontier of what's possible, a limitation of what's possible on this problem, given the inherent uncertainties in the underlying data, as well as any limitations to the current state of the art of machine learning. And then kind of as we zoom out and look at this across all the competitions that we've hosted, this is a very similar graph. And with the x-axis from 0 to 1 for the start of the competition to the end of the competition, then in this case, the y-axis is inverted with the beginning or benchmark at the beginning of a competition as 0, and the best score at the end of the competition as 1 at the top. And very quickly across all these competitions, we see the median competition dramatically improves at the beginning and then levels off at the end. With the simplest competitions are where we give people a single feature matrix and a target variable as operating near the top of the spectrum. And the most complicated competitions, those that involve computer vision problems or text data or things along those lines that are very rich structure to them and complex structure to them, as operating near the bottom of this spectrum where we see more consistent improvements over time. Then also, if we compare this to some applied machine learning research, it looks like competitions are running over many years instead of many months, where researchers operate with a set of standardized data sets and constantly publish improvements on those data sets. And one example of this is ImageNet, which is not hosted on Kaggle, but is an annual competition. And you can also plot the performance over time. For that competition, as you see, it's very dramatically dropped over the past 5 years with the advances in deep learning. And towards the end of a competition, one of the questions that I ask many times is, can we do better than this? Or is it possible to do better than the best results that participants submit? In most cases, the answer is no, in the sense that if I take the top submissions or top teams and ensemble them, I don't generate a performance improvement. In some cases, the answer is yes, and those tend to be on the problems, again, that have a very rich structure and human interpretable structure, such as grading some essays or identifying objects in images or things along those lines, where there's still improvements to be eked out by ensembling different approaches and indicating that we've not hit the limitation of the state of the art of machine learning there yet. Now let's take a step back and look holistically at some of the lessons that we've learned across all the competitions. But let's see, just to give you a sense of how these are split off, we've run about half the competitions involve some form of classification, either binary classification or multi-class. Most of the rest involve regression, and we've run a small number of optimization and ranking problems. And some of the characteristics that we see for participants that do well in competitions is, first, they set up their environment to enable really rapid iteration and experimentation. If you look at a standard machine learning processing loop, it involves identifying and handling the data oddities and understanding the problem, then moving on to data pre-processing, extracting and selecting features, training models, and then evaluating and visualizing the results. The best people in the competition look at this loop and go through it as fast as possible and tend to win by how many times they can get through this cycle and what their rate of improvement is, instead of the ones that go off, kind of think deeply about a problem, spend 2 months trying to implement one idea, then ultimately submit it, then find out it doesn't work. So if you're exploring the trade-off between reasoning from first principles versus experimenting and trying many things and seeing what works, the ones that work best for machine learning tend to be very heavily on trying many things and experimenting as rapidly as possible. And then there's great tools like Git or version control for code or machine learning libraries like scikit-learn and Python that really facilitate this. And as just one example for some of the tools that people build to help them solve competitions, this is a dashboard that one user used to evaluate his models in diabetic retinopathy, where this dashboard told him everything he needed to know about his model's performance, and he used this when he was comparing many different possible models and exploring the problem domain. Secondly, successful users really invest the time, thought, and creativity in problem structure and feature extraction and spend most of their exploration and experimentation on this division. Right now, we are in a state where there's many well-architected machine learning libraries for training machine learning models. It's very trivial to take a feature matrix, throw it into a large set of machine learning models, and evaluate the results. On the other hand, it's very hard to say what features you should be using, or as Xavier was talking about, what would be reliable features and strong features and interpretable features. So that's where data scientists should be spending a lot of time, really investing in that and understanding that. And to the extent that you have one or a small number of hammers to choose from, we've seen random forest and gradient boosted machines work very well as a generalized hammer across many common classification and regression tasks. You tend to operate very strongly by taking a GBM, throwing it at the problem, and having it work reliably. And on a more specialized set of tasks, deep learning should be our second hammer for anything that involves computer vision competitions or computer vision data sets, as well as certain types of text data. And if we look at some libraries that we've seen really commonly over the past 6 months for Kaggle competition winners, the two most common have been XGBoost, which is a nice, efficient implementation of gradient boosted machines, and Keras, which is a really flexible deep learning library. And if I go through and look here, about half the competitions in the past 6 months have leveraged one of those two or a combination thereof to win. Users have leveraged those to win those competitions, and part of the reason for that is they're incredibly flexible libraries and that you can quickly iterate and quickly experiment with them. Another common one that we've seen, this one's a bit less well known, is something called the Bruta feature selection algorithm, which is a really robust and reliable way to ask the question, is this feature actually adding value in my model, and am I learning something from this feature? It's a wrapper method around random forest, and it's calculated variable importance. And if you want to use it directly, the Bruta package in R is a good way to get started. And then Xavier spent a lot of time talking about this. I'll echo, or I fully agree with every lesson that he communicated, and this one was the one that really jumped out to me as the single strongest message we've seen from running Kaggle competitions. Virtually every winning method involves model ensembling, and it almost always results in marginal but meaningful and significant performance gains. There's a quote that every model is wrong, but some models are useful. So model ensembling is a way to average the wrongness out across all of your models and end up with something that's more reliable and more robust than it otherwise would be. And then one of the challenges that we face, both in designing competitions and running competitions, as well as our users face when they're trying to optimize machine learning models or learn from the data, is data leakage, or accidentally leaking information about the target variable that you're trying to predict into the main problem, and then learning based on that leaked information as opposed to the features that you want to learn on. And there's no good kind of first principles ways to control for this, but you constantly have to ask the question, is my model performing right? Does this make sense, et cetera, which really relates back to the importance of model debuggability, as Xavier had mentioned as well. So now that I've covered some things that competitions, or some of the lessons that we've learned from competitions, I also want to cover some things that competitions aren't really effective at. First, partly because of model ensembling, competitions don't use simple and theoretically elegant solutions. they usually yield models stacked up on top of models, stacked up on top of models to really squeeze the last possible amount of signal out of their problem. Secondly, they don't typically yield production code because of the rapid iteration and exploration that participants will use, even though I've seen a surprisingly amount of production code in other companies that also looks like this. And they don't always yield computationally efficient solutions. Right now, we're rewarding machine learning model performance without any computational or complexity constraints, which means that the solutions tend to be slow to train and slow to run. But many times we look at that as a difference between a data science problem and an engineering problem. Given like a way of figuring out what the best you can do in a problem is, it's usually a more straightforward approach to backtrack. Here's an efficient way to implement that within, say, a 1% improvement or 1% of the best possible result. And then they tend to be highly effective, on the other hand, at first, optimizing a very quantifiable evaluation metric by exploring an enormously broad range of approaches. One of the advantages of structuring it as a competition is that you explore every approach under the sun by doing that, as opposed to with a small team only exploring a narrow number of those. Secondly, they're really good at fairly and consistently evaluating a variety of approaches on the same problem. One of the challenges if you're looking at a lot of academic results is that implementation really details matter, which can make it tough to reproduce results in other settings or where the data or code isn't open source. Now, a second tip that I'd gotten from applying machine learning successfully was go to your domain, read the papers that apply to the domain, then figure out what that stupid baseline method that everything claims to beat, and then that stupid baseline method will inevitably work very well for you. Another thing that they're really good at is, to the extent that there's data quality or leakage issues in your data set, they're really good at identifying them. A couple examples of those. One of them from before Kaggle is whether KDD competitions involved breast cancer identification. Turned out the ID variable was very predictive in that from how they'd order the data set. And secondly, in one of the competitions that we hosted, one of the data sets that we got from the host used a stratified sampling method to create the data, and it turned out that the even numbers were one class and the odd numbers were the other class, which wasn't a very useful feature for solving the problem, but was an excellent feature for winning a competition. Then, in a similar vein, some of the other types of ways we've seen leakage emerge is from not properly handling time, from having some duplicated rows or duplicated results, so you have the same example end up in the training set and the test set. Then from a quality perspective, we've seen things like one of the essays that we got had a transcription error in it where the transcriber didn't follow instructions, so it said, this essay got good marks, but as far as I can tell, it's gibberish. And the grade for that was 5 out of 5 and 4 out of 5, so really, really strong grade. Or in another case, we've seen planes take off before they land, or land before they take off, I mean. Then another thing machine learning competitions are really good for is exposing specific problem domains to many new communities around the world. So taking a large community, then really focusing it on EEG problems, which previously had only been focused on a small subset of people, or a physics problem on exploring the Higgs boson. Now I'm going to take a little shift from there, and I want to talk a bit more about where Kaggle's going. So Kaggle's mission is to help the world learn from its data, and the machine learning competitions are a great starting off point for that. We're trying to grow far beyond that. Right now we're building a public platform for collaborating on data and analytics results, which really involves three things. It involves people, our community, it involves the underlying data and the data sources, and it involves the code that's used to create the analytics. And then we've released a really early alpha version of this as Kaggle scripts, which you can go to our site now, and on most competitions, you'll see a new feature where you can click new script or new notebook and immediately drop into an R, Python, or Julia environment where the data is preloaded along with all the statistical libraries you need to start working on a problem or analyzing a problem. And then one thing that's unique about this is every time you press run or every time you use this platform right now, everything's published immediately. So it means that we're creating a very rich library from our community for how they approach problems, both from an exploratory and analytics standpoint as well as a machine learning standpoint. And you can dive into those results very quickly and very early, as well as if you want to reproduce or build on someone else's results. Instead of installing 10 different Python packages and spending hours and hours trying to duplicate their environment, it's a click of a button away. And then to extend this, we're starting to enable users to do this in non-competition data sets. So starting to post a small number of curated data sets on Kaggle, things like census data or data on a lot of different colleges in the US that the US government releases. And then soon we'll be able to opening this up to any user. So any user will be able to publish data through Kaggle for subsequent analysis. Let's see, and I think I'm out of time now, so thanks a lot for taking the time to listen to me. And I encourage you to head to kaggle.com/scripts to check out the code and visualizations and results our community has created. And let's see, do we have questions or no? Thank you.